All right, so the next unit is on functions, primarily linear functions, but today is kind of an introductory lesson to what a function is. So I don't know if it's the best way to describe it, but the easiest way to describe it would be to just tell you a function is a fancy word for an equation. So tell me, what are some things we already know about an equation? Very good. It has an equal sign. And guess what? A function can also be expressed using an equal sign. What else do we know about an equation?
There's a variable.
Very good. There's a variable that we solve for. And also, I want to point out something else you said. There is a variable, which would imply that there is one variable. Yes, and on the equations that we work with, they all had one variable. A function is going to have two variables. And take a wild guess what the two most common variables used are.
Addition and subtraction.
Why is that a variable? A variable is a letter. X and Y.
Yeah. So, anyways, there's going to be three main things that we do with functions. Today we're going to evaluate them. That's towards the end. Before that, we're spending a lot of time learning some of the characteristics of a function, but we're going to evaluate them. Tomorrow we start graphing them, and then we should also probably write in a third one. We're also going to learn to write them. We're also going to learn to write them. But now these two, the graphing and the writing, are going to be limited strictly to linear functions. And since one of the things we're going to do is graph them, and graphing is a visual medium, what do you think the graph of a linear function is going to look like?
It's going to be straight.
Or you could say
It's going to have a line.
it's going to be a line. It's going to be that's you're obvious. So because we have two variables, typically x or y, and you should have already been exposed to function notation. We'll talk about that more today. Sometimes this can be used in place of a y. These are just some common words that are used to describe each of those variables. And we'll expand on that a little more as the lesson goes on. I've been having some issues with boredom today, so we'll touch on these as we go through it. On the bottom of this first slide is a graphic, it's a diagram that I've had for a while, and I kind of like it because, all right, look, when you have those two variables, maybe I've implied so far that that is what constitutes a function, but that's not necessarily the case. In order to be considered a function, you have to pass a certain test. Okay, the sake of just having two variables, all that does is make your equation a relation. Every function is also a relation, but not every relation is a function. In order to be a function, it has to pass a certain test, right? Well, the test that you have it undergo depends on how it's being presented to you. These are four different ways of representing, of displaying a relation. Let's go to the one that I would consider to probably be the most familiar to you, which is the ordered pair. Okay, we've seen ordered pairs before. You guys might call them points. They're arranged in x, comma, y, right? Or input, comma, output. You saw those words up here, input and output. How many points do you see?
4.
Oh, hey, that's an X and a Y.
Yeah.
I'm thinking like that.
There's 4 points. So really what's going on here is there are 4 different relationships. Okay? Meaning in this relation, when x is -3, y is 4. When x is 3, y is -1, 4, -1, so on and so forth. That same information is being given to you 3 other ways. The exact same points. So this is what I like about it, because you can compare and contrast. Of all these 3 other ways, which one would you say is the most reminiscent to ordered pairs?
What is reminiscent?
Close the most similar. Yeah, I'd say a table of values, sure. Everything looks exactly the same, but instead of parentheses and commas, We're using columns and rows. But I would say, and notice, because I want you to compare and contrast. Look at how the numbers are exactly the same. Have I confused anybody yet? It's just a different way of presenting, that information. Okay. I'd say the next most common, like familiar to you, form would be the graph. Okay, a graph has two axes, an x and a y. We'll start off at the origin. Has anybody here never plotted points before? Nicolia, have you plotted points before? Would you consider yourself to be an excellent plotter? And if you do know how to plot points, notice how the 4 points that you see plotted there are these exact 4 points as well. Now, the one that we probably have the least amount of exposure to is a mapping diagram. Now, the mapping diagram might look like a table of values because they're both kind of arranged in columns, but what appears to be the difference between those two? What about it? Okay, pay attention to the arrows. That's good. Yeah, we do have the use of arrows. We'll talk about that. What else do you see that's different?
They're not directly lined up with where they're supposed to go. What? They're not directly.
They don't
lined
have
up.
both fours.
The way that you treat repeated values. So like if you look at the table, on the inputs, I have 4s that are repeated, but on the map, I only see it once. On the table, I have a -1 output that is repeated. On the map, I only see it once. So, but Mr. Romero, there's 4 points though. So if you're not going to write something when it repeats, how would the person know that there's 4 relationships? Well, those are the arrows. So notice how we have a 3 with a -4, bam. Oh, sorry, a -3 with a 4, -3 goes to 4. A 3 with a -1, 3 goes to -1. A 4 with a -1, the 4 goes to -1. A 4 with a 3, and so on and so forth. Huh? Well, I'm glad. Her question is, doesn't that mean that it's not a function? Well, the next part of the presentation deals with when a relation is a function or when it's just a relation, when it's not considered a function. In order to be a function, think of it like dating. Now, we all can't be the type of ladies man that Adam is, okay? But let's say that you were faithful and you were a one-woman man like Kimon is. If each x has exactly 1 y, then we have a function. So the reason why, like Miranda picked up on the fact that this was not a function is she saw that 4 there on the input. That's kind of like the atom of inputs, and that 4 was messing around with the -1 and with the 3. So because one input gave you 2 different outputs, yes, it failed. Like these of these 4 ways, only 2 of these are supposed to be function tests, which is the mapping diagram and the graph. Those 2 are supposed to be the ways to test for a function. In my experience, I found that teachers have also been teaching kids how to use these. We'll get to that later. But it's supposed to be those 2. So as long as no x has 2 arrows leaving it, then you have a function. If each x has more than one, or if each one of them has more than 1 y value, then it fails the function test. These are the 2 function tests. So one of them is the map. The other one on a graph is called the vertical line test. You might remember that as well. If I go to the same graph and I were to draw a vertical line, since I have a computer, I can actually use a vertical line. You would probably have to use a ruler. So if I were to get a vertical line and go across, as long as I can make it across the entire graph and never touch any point twice, then I have a function. So far I'm doing good, Yeah, I only touched one, good. Oh no! I just epic fail. Yeah, I touched two different points with one vertical line. So, yeah, that means it's not a function.
The eggs on the right hand here.
Well, that brings us to the next one. Yes, what? Because I guess these two concepts tend to be way too complex. In my experience, I found that teachers just teach kids look straight at the table of values. If any x repeats, then you don't have a function. You fail. The y's can repeat. Notice how there's nothing wrong, even though this -1 does repeat. There's nothing wrong with two different arrows reaching the same y. You just can't have two arrows leaving the same x. The x's have to be faithful. Any questions there? Georgiana? Okay. So now let's go to domain and range. On the first slide, you already saw that we mentioned domain having to do with x values, and we mentioned range had to do with y values. But it's more than just that. Okay? Domain is a set of all x values. Y is the range is a set of all y values. What do I mean by set? What's another word for set? If I'm talking about a set of something.
Place.
I'm thinking of another
Group.
Yeah, I was thinking about group. Those words tripping. Well, pair is a very specific group. A pair just means two. But a set can be more than two. It can be anything. So there's two main ways to express these sets, these groups. One is set notation and one is interval notation. And they can be used interchangeably, but also from my experiences, depending on the type of function, one tends to be used more than the other one. So the way that we would differentiate between the two is to determine whether our function, and feel free to write this in because it's not there, like any Papa Romero has given you all those lines on the side that you can write this stuff in. You're making me write my own notes? How dare you, sir? How dare you?
And what does it decrease?
Discrete. The other word says continuous. If today, as a warm-up activity, when you walk into the room, if I would have had those two words written on the board, and I say, hey guys, try to define those words. Your life depends on it. You have to define one of those words, and your life depends on it. Which is the one you think you would go for?
Continuous.
I'd say probably continuous as well. So let's try with that one first. If you were to define something as being continuous, how would you define it? Continuous.
Never stop.
Well, you've been the closest with that one, but I wouldn't say never stops. It definitely doesn't mean that something is infinite. When something continues, it doesn't necessarily mean that it repeats. Yeah, but we don't want to use the same word in the definition. We want to try to use other words.
Keeps going.
Okay. You could say keeps going, but I feel that the better way to define it is that there's no interruption. Something that continues has a beginning. So let's write it begins and ends without interruption. No gaps. Not no caps, no gaps. What does W/O mean?
Win. I mean.
Win? No, it doesn't mean win. It doesn't mean win. Without. It means without. It means without. Whereas when a function is discrete, a discrete function does have gaps. Now that might be some confusing to some of you. So look, I mean, this is another oversimplification, but let's just think of this as a group of points. If you just see a group of points, you know, and you do see some gaps, that's discrete. So again, not because you have to, but just, I think it's kind of become customary. When you're going to write domain and range, when you're going to write a set of numbers that are discrete, typically we're going to use set notation. You don't have to. So like if you were to scrutinize it, oh, but I want to write an interval. Yeah, you could, but typically it's written in set notation, whereas functions that are continuous tend to be written in interval notation. What's the main difference? There are some differences, but maybe for you to focus on is the type of symbols they use. I've been impressed every single class today, including my favorite sixth period. At least one person has known what these are called. Let's see if you guys can make it 4 for 4.
Oh, no, brackets.
No, they're not brackets.
Braces.
Braces, very good. Those are called braces that look like elephant ears. 4 for 4.
So are we your favorite?
You guys have been up there with the favorites. Everybody except for the bees. Uh-huh. Oh yeah. Last semester, 7th period.
No, it's because Andy
And other people were also difficult, but they'll remain nameless. We'll protect their identities. Whereas interval notation uses these potential symbols. Now I've tried explaining it off of this slide, but too many kids get confused. So let's just stick to like I'll focus on the examples when we get to the examples. But for now, let's just focus on the symbols. What do you call the symbol that was above? Brace. What do you call these symbols? Parentheses or brackets, okay? Because these are typically used for functions that are continuous that don't have gaps, you would just have to write where we're beginning. This is the beginning, comma, and then you would write the end. And then we'll talk about when to use the parentheses. If this is not, oh, on the left there must always be a parentheses, and on the right there must always be a bracket. No, it's not. It doesn't work like that. Hang in there, Jay Bizzle. All right, here we go. Example time. This whole slide of examples deals with what we saw on that graphic. You are being presented a relation in which form? Which form is that relation being given to you? Yeah, these are ordered pairs. So let's just get those exact same ordered pairs and let's write it in the 3 other forms. Miranda, you've been great today. Which one of these would you prefer to? I'll pick on you next. Let's do the table, sure, because the table is almost as likely you just write everything exactly the same. -2, -1, 3, 3, 4, 3. Easy peasy, lemon squeeze. Keymon. Key is the mon. Well, which one do you want to do next? What do we call that? What?
Right. No, it's like that one.
Like it literally says it. If you actually look at the paper, it tells you the names of all the different. Well, it's called a mapping diagram. They cut off the word diagram. Now, but okay, if we're gonna use the table to write a mapping diagram, What difference do we have to account for? Yes, Mohammed. No, that's all. X is always domain and Y is always the range. Or sorry, I'm sorry. X is always input and Y is always output. If any number repeats, you only write it. It's Mohammed. Negative 2, 3, 4. Yeah. But then how do you express the relationship in a mapping diagram?
The 3 and the 4 we need to point to the
And the 4 and then 7, 8, 9.
and then negative 2, 1.
Jeanette, how do you express a relationship in a mapping diagram? Somebody mentioned it earlier and I go, oh, keep remember that because it's gonna come up later. It starts with A and ends with a row.
Arrow.
The arrows, yeah, use the arrows. So negative 2 goes to negative 1, 3 goes to 3, and then 4 goes to 3. The last one would be a graph, just plotting to the points, negative 2, negative 1. This right here, 3, 3, and 4, 3. It is 3, 3. This does not ask you here anywhere. It does not ask you if this relation is a function, but just for fun. Why? What are some justifications?
Because each X has one output.
Okay, you could say that every X only has one arrow leading it or one output. That's good.
Alright, so if you do the line test and go all the way across.
Very good. You can use a vertical line test to say that a vertical line can go right across and never touch the graph more than once. Yeah. Or the overly simplistic one that some people can look at the table and say the X's don't repeat. Back to the sheet. Now they want us to write domain and range. So Adam, since you were actually paying attention on the last slide, is this function discrete or continuous? No, it's discrete. There's a bunch of gaps. It's just a group of points. So we should use the braces. And if you have the benefit of a mapping diagram, that's the one that it's going to closely resemble because for domain and range, if anything repeats, you only write it once. So what is the domain here? All of the X's that we see are just negative 2, 3.
Negative 2, 3, and 4.
Negative 1, 3.
Johnny, were you the one that was saying that this is what was so hard and you got lost? Have you been found? Not yet.
I don't get the discrete.
I don't get the bracket thing.
Well, we haven't got to that yet.
I mean, not the bracket, the brace. Wait, what is it?
The brace, it just looks like elephant ears.
Like, what's the difference between the parentheses and the bracket?
The difference is just saying whether you're writing something in set notation or interval notation. When you use the braces, what goes inside the braces is supposed to express the entirety of what your graph contains. You're supposed to be writing all the X's. Whereas in interval notation, this is most commonly used when we have a graph that's continuous. We assume that there's no interruptions in between. All you're writing is just the beginning and the end. But this graph here is not continuous. There's like, here, watch. Let's assume we're going from left to right. If I put my pencil down on the first point I see, could I get to the next point without picking my pencil off the paper? No, I can't. So it's not continuous, it's discrete. If I were to connect the dots, and like that's what the graph would have looked like, then yeah, it would have been continuous. Leculio, what's your favorite, discrete or continuous? You can tell me in any one of the 4 languages that you speak. I don't like this seat. This is my protest. And it's my peaceful protest. All right, I'll give you 60 seconds to do this next one on your own. See if you can do. This should not take you more than 60 seconds.
All right, shut up, Gator.
Wait, but when you do the range, do you write those?
On the table, you have to write them. The only one that you don't.
When you're like
Oh, for domain and range, no. If anything repeats, you only write it once.
just for domain or
For any of them. For any of them. Remind me at the end of class, I'm supposed to project a picture of the buses. Because today the buses, if you take a bus, they're out of order today. Remind me when I finish, because I'll forget. All right, so by now you should be done. It really is that fast. -1, -1, 1, 1, 2, 1, 3, 2. Well, if you plot the points, -1, -1 is here, 1, 1 is there, 2, 1, and then 3, 2. And then on a mapping diagram, all the x's are unique. So I write each one. For the y's, there's only 3 unique ones. So I just write each of the 3. And then when I do the arrows, and you're not being asked, but if you were being asked, is this relation a function?
Yeah,
Yes, it is.
Because no x's. Yeah, the x's aren't repeating. You can do a vertical line test and it doesn't cross over.
But he's going for some of Adam's babies.
What?
You were also asked to write the domain and the range. Let's do that. Is this discrete or continuous? It's discrete. It's just a bunch of points. So let's just write all the x's, but it's a few of you were asking if anything repeats, just write it once.
So what would it look like if it was continuous?
Be patient, my son. In the interest of time, these are also asking us for domain and range, but since these are also discrete, I'm going to skip the domain and range part, but I want to focus on this, especially since mapping diagrams are a type of function test. So look at the first mapping diagram. Is this a function, yes or no? And then tell me why.
Because the x's are repeating.
Okay, well, no, I wouldn't use the x repeating thing on a mapping diagram because an x is never supposed to repeat on a mapping diagram. You're supposed to only write it once. Good. Each input only has one output. How about B?
No.
Miranda is correct. This is no. Why is it a no?
Because an input is more
Very good. There is an input that has more than one output of. Which is that evil input that's breaking the law? Yeah, the one. Georgiana, how are we doing so far? Okay. These are tables. Really, what you're, I'm going to ignore the domain and the range part again. I'm going to assume we know how to do the domain and range. I'll start doing it again when we get to continuous functions, but I still want to work on this. Really, what you're supposed to do here is to create a mapping diagram. And like say, okay, look, all of the x's here are unique. Sorry, no, take that back. I'm sorry. No, they're not. It's just negative 2, 5, and 7, and then all of the y's are unique. So this goes here and here. 5.
Wait, the 4 and the 2 are what?
They're both positive and negative. So, right, negative 2 goes to both 4, but it also goes to negative 4. So that's why here's a negative 2.
Oh, okay.
So now that I've drawn you a mapping diagram, is this a function?
No.
Okay, you would write no, and then you write no because there are inputs that have more than one output. But like I've said, I think I've realized that a lot of teachers just, instead of having to tell you to do the mapping diagram, they just tell you, hey, do any of the x's repeat? Which x's repeat? Negative 2 and 5, but you only need one of them to repeat. So that's why that would be a no. No, there's 2 positive 5s. So you can write in the explanation on your own. I'm not going to write a mapping diagram here for this B part, but is this a function?
Yes.
And what would the x be?
The x's does it.
You can say the x's don't repeat. If you were to write a mapping diagram, every x would only have one arrow leaving it. Right, Mint? What do you like better? What do you like better, mapping diagrams or tables? Suresh, it's all your fault. You're making the kulia sleepy. If you stop putting your head down, I promise you I'll stop talking about you. Yay, look, you were asking about a continuous function. Yay. Now hold on. We're still going to answer the same question we've been answering on the last 2 slides about a function. But in addition to that, let's go back to doing domain and range so that we can understand how to do this here, right? Now, what makes this continuous? Well, if I go from left to right and I put my pencil down on the first point that I see, which if I'm going from left to right would be up here. Is it possible to get to the end of the graph without having to pick up my pencil?
Yes.
If I follow the road, yeah. There are no gaps in between. That's what makes it continuous.
Oh.
Okay. So let's answer the first question first. Now, on any graph, whether it's continuous or not, what test do we use to test for a function? Vertical line test. So if I get my vertical line and I scan across, did you just say you want to eat a BLT?
DLT.
BOT?
DLT. Oh, vertical line.
It is a
Bacon and lettuce and tomato?
That's a function.
Do I pass the vertical line test?
Yes.
Yes, I do. And really, that would be the reason where it says explain this, you would write past vertical line test. But because this is continuous, if I were to ask you, hey, how many points are there just in between this beginning and the end? And there's an infinite amount. There's an infinite amount because there's like decimals and decimals and decimals and decimals and decimals and fractions, however you want to call it, rationals and irrationals. So there actually is a way to write this, believe it or not, there is a way to write this with set notation. But more commonly, we just use intervals, where we just want to write the beginning and the end.
So what if it's like that?
Hold on. Okay. Now, on a separate issue, okay, this is a separate note. I believe that when this was printed, okay, this was supposed to have arrows that got cut off. So this has nothing to do with what we've already answered, but it is going to affect the domain and range. Go ahead and put arrows up here. What does the arrow mean? It means that it continues. That it just keeps on going forever in that direction, right? So, all right, let's start off with domain. Domain deals with x. Range deals with y. So if x goes from left to right, okay, and we know that this is continuous, we always want to, we're going to use interval notation. This is what you were asking about, though. You don't get the brackets and the parentheses, okay? Where do smaller x's go? Because we always want to go from least to greatest.
Negative infinity.
What direction? Give me a directional order.
Up.
Up, x. Left. They go left. If it goes left to right. So, okay. So if I look at the left first, I realize that I have a limited amount of space. But because of these arrows, if I had enough space, how far left would this go? It would only go to -6?
So keep going.
If I were able to pinch this and pinch this and pinch it and pinch it and pinch it and pinch it, how far left would this continue to go?
Negative infinity.
It will go forever. So the beginning of this graph from left to right is negative infinity. Now, yeah, the difference between a parentheses and a bracket is a parentheses is used when you don't actually reach the number. If your graph is not actually getting to making contact with that number, then use a parentheses. If you do reach it, it's a bracket. Can you ever reach infinity? No. So infinity is always going to carry a parentheses. Comma. Okay, now let's go on the big end, which is on the right. If I gave this enough space, how far would it go to the right? Positive infinity, which also cannot be reached. So that's going to take a parentheses. Right, Vincenzo?
Is that always going to do that?
It depends on the graph. You'll see what. You'll see what. We're going to do this again on the bottom. Let's go with range. Okay, range is how high and how low, and here's where I get most of the problems because we have to fight bad habits, right? We're used to looking at a document and scanning it from top to bottom because that's how we learn to read. We learn to read from top to bottom. But when you write in interval notation, we want to go from least to greatest. So when we're talking about range, that's from bottom to top. Now, you get kids that are already kind of confused, and this diagram, I hate this diagram, because really, if the first question I'm going to ask you is, well, how low does this go? And if you look at it exactly how it is, this turning point there, on both of these turning points, it's not really reaching that line, which is the -8. So the answer really is that we don't know how low. There is no way to know how low. But just for the purposes of understanding, can you just pretend? Let's just pretend. Let's get our magic eraser. And let's pretend that this graph actually clearly went down to -8. Can you just do that for me? Let's just pretend that that's the way it was drawn. Okay? And then now I ask you, how low does this go? What would you say? You would say -8. Is it touching the -8? Now, the way that I've drawn it now, is it actually making contact with that -8 line? Yes, it is. So I would write -8, but I would write a bracket because it actually is reaching that point. Comma. Oh, now for range, I would, because it's continuous in between. There's no gaps in between. So now I just want the big end. And for the y that's up, those arrows are pointing up, so it is going from -8 all the way to. Have I lost you? Okay. Let's go to this next one. Let's first answer, is this a function? If I do a vertical line test.
That is not a function.
Fail. Fail. Now, we've already done domain and range for discrete functions like this, but since there's so many points, I think this is actually a good one to do. But because it's not continuous, let's go back to set notation. And let's see if you can tell me what all the x's are and then what all the y's are. You just take that off my desk? Were you drooling on the table or something? Is that what? Let's name all the x's. So like here, what's the x for the first point?
-6.
-6. Good.
-4.
-6, good. And then -4, perfect.
-2.
Then -2, Johnny, you're on fire. Keep on going. +1. Do you see what Johnny's doing? He's just going along the x-axis.
5.
And everywhere he sees a new point, look, -4, -2, 1. What's the next one? 5.
Do we have 2 5s in there?
And then 8.
No, just one. So he repeats what we read it once. And then 8. Good. How about for the range? That better not stay on my desk.
Range.
Let's go from low to high.
+8.
How low do we go? Let's go from low to high. Not because you have to. Yeah, -9. Up to 0. Good. Yeah, you guys see this point here? You want to write 8 again. Remember that 8 is the x. It should be 0, 3, 6, and 8. If you don't know right after the numbers, call those.
8.
I mean,
Wait,
oh,
Oh yeah, there is a 1. Sorry, thanks. Yeah, there was also a 1 there. It's my fault. Anybody else? Any questions there? Now you're gonna want to pay attention to this.
that is not a function.
Okay, to answer the first question, this is definitely not a function because it's going to fail the function test. That's what Mint is excited about. In several locations, everywhere in here it fails. So that's the obvious one. This is not a function. But is this continuous or discrete?
Discrete.
It's continuous because from beginning to end, I don't know.
Continuous.
So instead of expressing the domain and range using set notation, let's do interval notation. Let's start off with domain, which means x. How far left does this graph go? How far to the left?
-1.
It does not go to negative infinity. It goes to -1.
-1.
Does it actually reach the -1?
Yes.
Bracket. Comma. How far right does it go?
Alright, and positive infinity.
-1.
Right?
This is all -1. Does it make contact anywhere with that line? Yes, it does.
+3.
And then, how far right does it go?
+3.
3. Does it touch +3?
Yes.
But Mr. Romero, so then what? Every time it's a number, then it's going to be a bracket, and then when it's infinity, it's a parentheses. Many times, yes, but not necessarily. If these, remember when we did inequalities? If these points would have been open circles, then it would be a parentheses, because it means it doesn't actually touch. Naya and Naya only, give me the range. Remember to start on the low end. How low does this go? -2, because how high does it go, Naya?
It goes up to 3.
Good. And because it touches also.
Wait, so if it does touch, it's in parentheses?
But the only way it's gonna be a number and not touch is if you see those open circles. Guys, we're almost done. This next slide is supposed to be for graphing, but I'm not gonna use it for graphing. What I want to use it is an introduction into function notation so that we can get to evaluating, which was one of the things that we said we were going to do today. Probably the most important thing we do today. Euro quotation. And if you meant by parentheses, yes, that's the important thing. Because look, how many variables do we have in a function? 2. So when we're evaluating, which is what we're about to start doing, there's 2 variables, they're going to give you 1. You're going to be given 1, you have to find the other. But you can't find one if you don't know which one they're giving you. So the ones in the parentheses, not the quotations, but the parentheses, those are x's. The ones that are by themselves on the side of the equal sign, those are y's. Now remember, like this is meant to be for graphing, but I'm not going to graph these. But if I were to graph these, I would just be graphing here negative 1 comma 1, 2 comma 7, 1 comma negative 1, and 3 comma 0. But I'll use the graphing fun for you.
So it's not like an actual question like A, B, C.
No, these were just meant to graph the point, plot the point. But if you understand which are x and which are y's, now we can get into function evaluation.
Oh, isn't this where you just?
What do all of these mean?
Why?
Yes, shh. All of these mean y, but when you write them in function notation, it's just a way to give it a name. The same way, like Johnny is a name, or Hameth is a name, and Frankie's a name, and Greg is a name. Those are just names. So here the questions are A, B, and C. I see a 10 of them. There's two variables. They're going to give you one. Because they wrote the 10 in the parentheses, what does that 10 count as? It counts as an x. So what they want you to do is get a 10 and put it into x in Greg. G. So I would write negative 3 times 10. Can we please be quiet so I can finish? This used to confuse me when I was a kid because since middle school I have been taught, hey, parentheses means multiply, parentheses means multiply, parentheses. So I wanted to multiply here and put like 10G. But no, like I'm not gonna do, when you do evaluation, all your work is on one side. So I'm not gonna do anything on the left. The left just stays G of 10. What's negative 3 times 10?
Negative 30.
Plus 1 is?
Negative 29.
Negative 20. Oh yeah. This next one, this 3 counts as an x. So they want you to get the 3 and put it in for x, but only into Frankie. You're nice. So 3 squared plus 7 is minus 16. On this last one, they want you to put in negative 2 into Harold.
Negative 6.
So 12 over negative 2 is nothing. It might have gotten cut off. I don't know. I don't remember. In this case, yeah, you don't do anything with the J. If we skip a slide for the sake of time, because the slide right after was the same thing, notice how now the number is not in the parentheses, it's on the other side. So what do all of these numbers count as?
Y. I mean, X's. I mean,
You want to be a sailor?
You basically like do an 8
Okay, answer my question first. Because they're not inside the parentheses, what do these count as? These count as y's. Well, guess what? All of these we already finished saying also count as y's. So this is telling you, hey, get this whole entire g of x, get the whole g of x, take it out, and replace it with a 16. And now guess what? This becomes just like the equations we did last year. Minus 1, 15 is equal to negative 3x.
negative 5. Wow.
For h, get that negative 2 and put it in for all of it. Take this h of x out. Take everything. Take the entire h of, and look, notice how it's even telling you, find x. If you're finding x, they're giving you y. So negative 2 is equal to 12 over x. Now you might think this is easy because, oh, this is only one step. Take it off. Take it off. You don't look that much sillier than you normally do, but it's a little bit silly. When a variable is in the bottom of a fraction, it can be tricky to solve for. So what I would tell you to do is to write this as a fraction also. And let's see who's learned something this semester. What do you call it when one of you?
Reciprocal.
What's called a proportion, but you cross multiply. Yes. Negative 2x is equal to 12.
I thought you like
cross products. Divide by -2 like you do in the hood. Notice how in each case, what variable are we solving for here? Which variable are we solving for here? X. Finally, the last one. 23 is equal to 2x plus 9. Put in the 23 where the j of x is. Minus 9 minus 9. 12 is equal to 2x divided by 2. 6 equals x. Remember that this week there's no laptop, so don't waste time on lies. No, you check it. I think it's Khan Academy.